Our next speaker is Aditya Grover. He's a postdoc at UC Berkeley, and fall 21, he'll be at UCLA as an assistant professor. And he's currently a Google Research Fellow in the Probability Program. Aditya?
Hi. Thanks, Prasad. So today I'm going to talk about some recent work at ICML on trying to do fair data generation without labels. And this is joint work with Christy, Choi, Trisha Singh, Reshu, and my PhD advisor, Steph Normon from Stanford. Next slide, please. Okay, so recently we've been seeing a lot of different applications of generative modeling. So we have seen very high quality images. We're also seeing a lot of applications of these models as applications in scientific domains. For example, MRI for trying to optimize for drugs and materials. And if you think about all these applications, the core technology that powers it is trying to learn a generative model. Can you go to the next slide? So we can think of the generative modeling problem as follows. So there is some data distribution of interest. So this could be a set of samples we have from images, from text, or from graphs, and we're interested in trying to learn this distribution. So the procedure that is typically followed in getting these impressive results that we saw in the previous slide is to think of some model family M and then try to find some member of this family, which minimizes some notion of discrepancy with respect to data distribution. Next slide. So what I want to talk about today is a problem which I think is of increasing relevance to both industry and as well as theoreticians here, which is to think about what happens in the practical scenario where we might have only very few samples with respect to the data distribution, but in this unsupervised context, we might have a lot of different data sets which can help us learn something about this target data distribution. So the key question that I'll be focusing on is that how can we leverage data sets which do not come with any label information from different data distributions to try to then approximate a target data distribution P data. Next slide. Now, to give a sense of why this problem is of interest, I think this problem has direct implications for fairness. So recently we have been seeing a lot of these different successes of these models where you can scrape internet scale data and then train very large models. But the upside of doing such large scale training is that when you look at the examples that you generate from these models, you see that these samples have inherent biases. So this is a state-of-the-art generative model that's trained on facial images, and we can see that there's a different proportion of facial images across the subpopulations, which can then propagate stereotypes. Next slide. So the key contribution of this work was to propose a new density ratio estimation technique, which then is able to mitigate the kind of the biases that we see previously, in which we have auxiliary data distributions and we are trying to see how they differ from the target data distribution without requiring any notion of labels. So I'll not go into the analysis, but just to list it out here, and I'm happy to chat about it in the breakout rooms. We essentially do a bias variance analysis of our estimator and show that it scales much better than previous estimators for high dimensions. And in terms of the practical algorithm, this algorithm requires no label information from the different data distributions about the source of bias. It's sample efficient as well in real world domains, and it applies in a model agnostic fashion to large families of existing generative models, such as V's, GANs, and autoregressive models. So this is also a preview of the results when we actually employ this technique, and we can see that it achieves a favorable split in across the two subpopulations that we care about. Thank you.